Free-falling objects are one of the most studied concepts in introductory physics, and they have a natural analog to calculus, which we can't really discuss at this point because we need some more techniques. But effectively what we have is if I have some object, and at some starting time I'm at some place, and let's say I throw an object in the air, and I let it go up and gravity takes over and it comes back down, you know, what goes up must come down sort of thing. I want to say, well, I want to model that. I want to figure out what in the world is happening here. So it turns out that we can come up with a fairly straightforward equation, this equation, which describes the position at any time based on some initial conditions. So if I have some starting position, S0, then what this function tells me is that at time 0, if I plug in 0 for t, this term goes away and that term goes away. So that dominates. Or that's the only term. So I'm at my starting position. And if this velocity is positive, what this tells me is as time goes on, it's trying to push the position upward. This velocity is negative, it's trying to push the position downward. But beyond that, what I have is this negative 1/2 gt squared. The problem is at t squared, you know, like time equals 10, for instance, this becomes a 100. And this becomes, you know, this is only 10. So over time, this gravity term will eventually blow up and will always drive it into the ground. No matter what, no matter how large V0 is, that t squared eventually takes over and again just drives it into the ground. So V0 is a starting velocity, but this g is the gravitational acceleration. So that's usually represented either by 9.8 meters per second squared if you're dealing with some sort of metric problem set, or 32 feet per second squared if you're dealing with imperial. And, you know, so if your problem is given in feet, use this one. If your problem is given in meters or centimeters or whatever, use this one. And what we'll do is we'll just plug in those constants into this function and we'll kind of generate a function that models the position of the object we're dealing with. So anyway, to do that, what we have is a case where a diver jumps from a platform 32 feet high, and he's doing it at 16 feet per second. So he launches pretty quickly, or, you know, pretty forcefully. And we want to find when he hits the water. Well, when he hits the water, that's probably going to be at position 0. That's going to be a height of 0, because he's 32 feet above the water. So if that's true, then I'm going to say my initial position is 32 feet and my initial velocity is 16. And since those are feet, it makes sense to use the imperial 32 feet per second. So if I construct that function, I get s of t is negative 1/2 32 t squared plus 16t plus 32. Now this is going to turn out to be negative 16. So why don't I factor out a negative 16? And write the function that way. And the reason I'm trying to do that is because I'm trying to find when I hit the water. So I'm trying to find when the output of this function is 0. So ultimately, I'm trying to solve this equation. So since that's factored, I can divide both sides by 16. And then I have to solve this equation, which I can do with like the quadratic formula, or I could factor it. And that gives me two answers, t equals negative 1 and t equals 2. Now t equals negative 1 doesn't really make sense, because t equals negative 1 means we have some sort of weird time machine. Because if he launched at 16 feet, it would mean that like he went backwards in time and went through the platform into the ground. So that's just really odd. You would not expect that to be the case. So given that, you usually, when you're dealing with these problems, you're almost exclusively going to be dealing with the positive time step. So that tells me that the diver hits the water 2 seconds after he jumps off the platform. And then we want to find the velocity. So there's a couple things you want to think about. All right, his velocity. So is it reasonable to think that his velocity would be positive when he hits the water? Because if his velocity was positive when he hits the water, then he's coming out of the water. Well, no, he's going into it. So it's only natural to think that he's going to hit the water like this. And that makes sense because this is actually a parabola. So you're going to have a situation where you go up and then down. So your velocity is going to be negative. But let's solve to be sure. So if S of t is negative 16t squared plus 16t plus 32, then your velocity, which is the derivative of your position function, is negative 32t plus 16. And we want to know what the velocity is at impact. So the velocity at time 2 is negative 32 times 2 plus 16, which is negative 64 plus 16, which is negative 48 meters per second. So he goes up in the air, and the higher he goes up, the harder he's coming down at the end, because the more that acceleration is just driving him into the ground. So he may jump at 16 feet per second, but he's hitting the water 3 times harder than he jumped out. So, or not harder, but like 3 times the speed at which he jumped, which is kind of an interesting result here. But ultimately, these are how you solve these problems. You look at the model, you find what S0 and V0 are from reading the problem statement, and anytime that you're trying to find when it hits the water, you're looking for the output of the function.